Okay, Conceptual Geometry 4.1, Classifying Triangles. The objective, students will be able to identify and classify triangles by either angles or sides. So, a couple things here. When naming a triangle, we name it by its vertices. These are the corners of the triangle. So here we have corners A, B, and C, or vertices A, B, and C. So we would name this triangle as triangle ABC. Alright, so let's go through a couple definitions here. I'm not going to spend a ton of time on these, because these are things you've probably heard before. An equilateral triangle, this is when all the sides are equal. And we'll find out later, that means all the angles are equal too. Isosceles, at least two of the sides are equal. And scalene, all the sides are unequal, so they're all different. Acute, all of the angles are acute in an acute angled triangle, which means they are less than 90 degrees. In a right angled triangle, we have only one. Notice we had all angles in acute, but in a right angled triangle, we have only one angle that is a right angle, or equal to 90 degrees. Put a little equal sign there. And an obtuse angled triangle, one angle is obtuse. Again, just one is obtuse. Or we would say greater than 90 degrees. Alright. So we're going to name triangles that represent each one of these. I want you to go ahead and try and do that. Try and go through and see if you can name at least one triangle that is scalene, right, isosceles, obtuse, and acute within this drawing here. So there's triangles within triangles. So here I have BEC or ABC. So there's lots of different triangles here. See what you can name. And pause the video, and I'll put up the answers in just a second. Okay, so I have some answers here. This is not all of the answers by any means, because some of these have a lot of different things that can work. But let's just go through this. Scalene, ABD, we would say ABD is scalene because all the sides are different lengths, so it's a scalene. For a right triangle, I chose BEC, but you may notice that there are several right triangles in here that you can choose. Isosceles, I chose ABC, but I could have also chose ADC down here. Obtuse, I chose ABD, but I could have also chosen CBD. And for acute, I chose ABC as well because it looks like all of the angles here are acute, or less than 90 degrees. What I want to point out is, look, ABC is isosceles and acute. That's because we can classify triangle by both angles and sides. So we would say it's an acute isosceles triangle. It is both. And that's okay. You're going to see that a lot, that we can combine one term from the sides and one term from the angles to give us a more exact description of that triangle. Okay, let's go to the next page. Okay, here it says that I have triangle ABC. To the right is an equilateral triangle, meaning all the sides are the same. And then it starts giving me some descriptions of all the sides. Well, it says AC is x plus 9, BC is 3x minus 9, and AB is 2x. Well, if all the sides are the same, that means that these are all equal to each other. And if these are all equal to each other and I want to find x, I could just set any of these two equal. Well, I'm going to pick the two that look easiest to me, x plus 9 and 2x. 3x plus 9 looks like it'll be a little bit more work. Still doable, but just a little bit more work than x plus 9 and 2x. So let's just set those equal. Alright, I'm going to subtract x from both sides. And I would get 9 equals 2x minus 1x is just x. Boom. Easy. So x equals 9. Now, that's not the length of the sides, because remember, here's the lengths of the sides. So I could plug it into any one of these equations, and I should get an answer. Well, I'm going to use this one because I think it's easiest. 2x, so 2 times 9 is 18. So I know that all the side lengths are 18. Now, I didn't ask for that, but I'm just showing you that we could find it. So on this next one, I want you to use the same drawing. You may want to erase the 18 here and try your best with these new numbers. right? Because they have AC is y plus 3, 2y minus 4, and 3z plus 1. I would recommend not using the one with a z at first, and just using the y's at first. And then go back and see if you can find the z. So go ahead and try that. I'll put the answers up in just a second. Okay, so for this next one, I set the y's equal, or the equations with the y's in them equal, because they're both sides of an equilateral triangle. And I solved for y, and I got y equals 7. And then I wanted to figure out what each length of this triangle would be, so I plugged 7 back in. I used this one, y plus 3. I thought that would be the easiest. So 7 plus 3 is 10. That means that all the sides are 10. So since I have this 3z plus 1, I could just set that equal to 10, because it's one of the sides of the equilateral triangle as well, and solve for that, and I get z equals 3, and that's how I solve for both y and z. Alright. Example number 3. It says triangle EDF has the following coordinates. E is at negative 5, 3, 3, 9. D is at 3, 9, and F is at 2, 2. And we're going to classify the triangle by its sides. Well, the first step in these types of problems is to always graph it out. So plot these points. So I'm going to zoom in and plot E at negative 5, 3 first. Let's see, negative 5, 3, that's right there. My marker out and mark that. That's E. Okay, the next one is at 3, 9. So I'm going to go over 3 and up. 2, 3, 4, 5, 6, 7, 8, 9. I believe that was D. And the last one is F at 2, 2. Yep. Okay. And now that we have them all plotted, we're going to connect the dots to make the triangle. I'm going to use black to connect the dots. It'd probably be helpful to use a straight edge when doing this, just makes your life a little bit easier. And now what we need to do is we need to figure out the distance of all the sides. Do I have something in my arsenal of mathematics that tells me the distance from one point to another? And you should say, yes you do, the distance formula. Remember that the distance formula is d equals the square root x2 minus x1 in parentheses and squared plus y2 minus y1 parentheses squared. Okay, that is the official distance formula, but we're going to do a little bit of a shortcut, because really what happens, the x2 minus x1 is just telling me, hey, along this path, what's the distance from left to right? And the y2 minus y1 is just telling me, hey, along this path, what's the distance up and down? And since we're graphing anyway, we can just count, and I think it's easier. So if you want to use the distance formula, go for it. Just plug in the points accordingly. Or you could kind of do it this way. This is what I like to do. So let's zoom in on this triangle. What I like to do is I like to sketch off a nice, neat right triangle. So I'm going to, on the top side here, I'm going to just sketch a little right triangle, see? What the distance formula really does is it just counts or calculates the distance up and down and left to right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12. And on this side, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. Alright, that means that this distance is going to be, let me use a different color so it shows it a little better. It's going to be the square root of 12 squared plus 9 squared. And I can just plug that in for my number. So let's do the same thing on the other sides. It looks like I go over 1, up 7 here. So this distance is going to be the square root of 1 squared plus 7 squared. And over here, I go over so many, up so many, almost went over too much there. So it looks like I went up 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5, 6, 7. So this guy, this distance here is the square root of 7 squared plus 5 squared. I just think that's easier than the distance formula, but If you don't like it, you don't have to use it. Okay. When I go to simplify all these, let's see what we get. Okay, for ED, I would get 12 squared is 144, plus 9 squared is 81, so I'm going to have to add that up. That was 81, it's, let's see, 145 plus 80, it's like 225, so you get the square root of 225. And I think that actually can be simplified because the square root of 225, that is 15. Okay, so let's keep going. Let's do DF now. You know what? I just realized, and you guys probably realized this too, that I was graphing this thing wrong the entire time. That says negative 5, 3, not negative 5, negative 3. So that means I need to change where I put my E. I apologize. It's going to change everything. So I'm going to just say, let's ignore this example because I can't erase it on the video. And let's go to the next slide and I'll do the next one as the example. Sorry about that. Okay, let's see if I can plot some points correctly on practice number 3. This one says negative 5, negative 4. So this one is down here in the bottom. So let me zoom in and plot that. Negative 5, negative 4. And then the next one is 3, negative 4. So I go over 3, down 4. And the next one is 3, 7. Alright, now I connect all my lines. Okay. Well, this one's a little bit easier if you think about it because this distance is going to be really easy to calculate. I could just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is 11. Count this one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is 8. And if you remember on the last slide when I was doing the little boxing, if the coordinates were right, it still would have worked. Yeah, I was doing a little box off. Well, look, this thing is technically already boxed off. I mean, I could do it on the other side if I want, but I'm going to get the same numbers, 8 and 11. So that means that this distance from, this was my E, right, and this was my D, and this was my F. So this distance from E to F is just going to be the square root of 8 squared plus 11 squared, which when we simplify it is the square root of 64 plus 121, and 64 plus 121 is 185, square root 185. Okay, so we have 3 distances here. We have 180, I put 184. I'm not doing too good today. 185. Okay, so square root 185, I have 11, I have 8, so I have 3 different distances. So that makes this a scalene triangle. And there's something else you should have noticed right away. If I have one side going exactly left or right on the graph, and another side going straight up and down, isn't it safe to say that this is a right angle right here? So that would make this a scalene and a right triangle. Or actually, the better way to say that would just be simply a right scalene triangle. Okay. Yeah, sorry about the mess up on the last one. The math is still the same. I just plotted the point wrong, so we probably could have finished it. But last thing what you want to do for your summary is you want to try and see how many different angle side combinations you could come up with. So for example, a right isosceles, or like we had in this problem before, a right scalene. Come up with as many as you can and try to sketch out what they would look like. It's okay if you're wrong, just try your best, but there are some that actually do not work. So think about them as you write them out. Let me give you an example. We cannot have an obtuse equilateral. I said earlier that equilaterals have all the angles being the same, and if they're all obtuse, it won't make a triangle. If you don't believe me, try and sketch it out, see what happens. Okay, that's it for today's video. See you guys later.